Wayne Strasser at Liberty University using computational fluid dynamics to develop a punctuated equilibrium model to increase the feasibility of simulating polymerization reactions with complex kinetics and rigorous CFD so the chemical process behind a $45 billion industry can be optimized. This was originally titled Developing a Polymerization Reactor Reduced Order Model, but we changed the name of it fairly recently, and I'll get into a little bit why later, and this research is sponsored by Westlake Chemical. So first, a little bit into the current state of things. The polymerization reaction we are studying is low-density polyethylene polymerization. So LDPE is, of course, a very common and a very important plastic. As I said, it's backing a $45 billion industry used to make plastic bags, packaging films, bottles, toys, liners for milk cartons, and much more. And it is simulated, these reactions take place in either autoclave or tubular reactors typically. We're going to be looking at autoclave reactors, so you have that high pressure, high temperature, a central stir to mix, a low temperature monomer feed stream or ethylene to cool it down, a low throughput but a high variability. So these autoclave reactors are mainly for customizable polymers rather than such large throughputs. There are plenty of chemical or polymer softwares out there to simulate the chemistry behind these. Commonly, Aspen is one that we validate some of our research against. But these CSTRs, these continuous stirred tank reactors, often assume perfect mixing, which makes them very cheap computationally, but gives you very approximated results. Now, that's not to say these CSTRs are useless. We use them quite often in the development of some of our CFD models. You can see a CSTR right there. You have a typical inlet outlet and an agitator. But these CSTRs typically focus on the reaction kinetics, mass transfer, and the reactor performance metrics without resolving any spatial flow fields. So if you want to capture any sort of gradients of species concentrations, temperatures, viscosities, and so on, you need to use computational fluid dynamics. Now you can see on the right-hand side here, we have some contours of temperature in one of our industrial scale reactors. And you can see all these gradients of temperatures throughout the reactor. You see just zone 1 of the reactor, which we'll get to a diagram a little later, and then an axial view from the top. But these gradients can significantly impact reaction rates, molecular weight distributions, and other polymer properties, and neglecting to look into them with some of these chemical softwares can result in a lack of insight into localized phenomenon, process instabilities, and possible suboptimal performance of a reactor. Now again, these CSTRs are not useless. We are using them during our developmental phases rather than going into a reactor with millions and millions of cells for every little test we're going to do. We'll run these dozens and dozens of tests in CSTRs as a proof of concept of our kinetics in CFD. The unfortunate thing is that perfectly realistic chemistry within CFD is just unreasonable. If you wanted that, you would need a mesh on the length scale of molecules. In terms, or for polymerization reactions, you would need a partial differential equation for every chain length of polymer, and considering that can theoretically be an infinite amount of chain lengths, there's your problem. So even if you were to assume polymers of just a few thousand units for a chain length, which is a highly inaccurate assumption, that is still a lot of computational power that would be required. Now that's where the method of moments comes in. I'll give you a little bit of information about this just to be dangerous, but my colleague will be presenting a little bit about this and molecular weight distribution reconstruction in this room around 12:30. So the method of moments is a kinetic-based approach that reduces your infinite set of partial differential equations down to a finite set of moment equations. The cool things about the method of moments is it can be derived with any kinetic scheme, not just polymerization, and it's compatible with CFD, which is obviously a big thing if we're using CFD. The only issue is that it does not allow for the explicit calculation of the molecular weight distribution, which again, not a concern for this research exactly, but my colleague will be presenting on that later today. So a little bit more into the method of moments. So as I said, you take that infinite amount of mass balancing equations, convert it to a finite set of moment equations, but those moment equations are made up of live moments and dead moments, and the live and dead moments are made up of 0th, first, and second moments. Now, live moments are crucial for capturing information about ongoing reactions, while the dead moments are for characterizing the population that has already completed the reaction pathways. A 0th moment gives information about how many entities are present, live or dead. The first moment provides data on the cumulative size, and for reactions like this, that would be similar to your molecular weight. And the second moment gives insight into the distribution breadth or variability to calculate metrics such as weight average molecular weight or polydispersity index. Polydispersity index, or PDI, being the breadth of a molecular weight distribution, and that is our main metric in this research. So, Yoder and Strasser, in a paper that is currently under review, have combined their complex kinetics with the method of moments in a rigorous industrial plant scale model, which you can see a diagram of on the right there. We have 4 separate zones in our simulation. That central stir, the zones are separated by baffles, PIDs to control the reaction and flow from left to right. So our zone 4 is our outlet zone, one of the smaller ones, and that's the main zone we are going to be simulating in CSTRs in this research. So right now, they have a simulation almost capable of reconstructing the molecular weight distribution with all of these components added up. So that's all great, but why do we need this research? What is a punctuated equilibrium model, or a PEM, doing for us? If you see here on the right, we are looking at PDI versus flow time. These PDI values have been omitted as requested the sponsor, but you can see that at that red vertical line, we have the start of a fit curve. We've only simulated around 400 seconds of flow time, and that's because we're simulating around 2.7 seconds of flow time a day. And as you can see from the fit curve, we would need somewhere in the realm of 2,000 seconds of flow time to reach a converged kinetic solution. And if you do that super complicated math, that's around 2 years of Earth time to reach a solution, and that's something we don't want to have to wait for. So implementing a PEM, we can temporarily freeze equations in our solver not being used during kinetic development. So if a flow field or turbulence is at quasi-steady state, aka if the very small changes with time of the flow field and those repetitions of those small changes are very repeatable and not changing a lot, then you can essentially freeze the flow field, simulate the kinetics, and you will end up with PDI calculations that are unaffected by the flow field that is frozen if it is at QSS only. You will also get an unaffected flow time to QSS, but if you are disabling a ton of equations, your solver is going to be moving quicker. So while it will take the same amount of flow time, those calculations will be faster, so you'll get there at a decreased Earth time. We're accomplishing this using commercial solver ANSYS Fluent, and here just your incompressible governing relations, your continuity, momentum, and energy equations, considering the components of both laminar and turbulent flow. And you'll notice, of course, you have the source term down in the energy equation for these exothermic chemical reactions that are going on. So this is the plot we were looking at earlier, but we've overlaid a hypothetical PEM calculation onto it. So this highlighted data is completely arbitrary, but just being used to demonstrate what this might look like. So each of those flat portions of the stair step, as we'll refer to it as, is being simulated when there's a half dozen equations in our solver frozen. So at every flat point on this plot, your solver is running significantly faster. And so again, while you're still around that 2,000 flow time mark to a converged solution, you're getting there quicker. Now, as I mentioned, we are using CSTRs for this study. We coarsened the CSTR to the point that we didn't believe was possible at the beginning, and that is another paper that is in preparation, but I'll give you a little bit about it now. So we started with a CSTR of around 65,000 tetrahedral elements, and we used TETs on purpose to make it more numerically diffusive. We wanted that perfectly mixed CFD CSTR, so more numerical diffusion, the more mixed it'll be. But this didn't take 2 years to run to convergence, but it still took 2 weeks, and when we were running dozens of tests, that was still a little bit time prohibitive. So we wanted to coarsen it, and we're curious how much we could coarsen it. So our next CSTR had around 4,300 elements. Now with hex cells, because they're just more effective in regards to space, we'll use less of them. We got good results, less than 0.3% error from our target PDI. So we coarsened it more, down to around 1,000 cells, good results, down to 29 cells, still have good results, and we coarsened our CSTR down to only 3 cells in CFD. So each of these CSGRs has an inlet outlet and a mixing zone, and each of these mixing zones has the same volume as each other and as the zone 4 of our real reactor. In addition to these, we have 2 more of just these meshes, but adapted to give us more data as we are testing between varying cell counts. To calculate QSS, we will take a window of some amount of time steps, and if the maximum PDI minus the minimum PDI within that zone is less than some threshold, and if it doesn't exceed this threshold for the remainder of the data, then you're at QSS, pretty much telling us that QSS is no longer significantly changing. Here is our PEM design of experiments. So we've run 9 cases currently, and we can disable the flow equations, turbulence, energy, the transport of all of our species, both catalysts, propane, and our monomer ethylene. And we can even disable the equations that calculate our moments because they're implemented as user-defined scalars in our solver. And so flow in this case is referring to pressure velocity coupling, and it will disable the continuity and momentum equation calculations. So take a note at C2, C6, and C9. Those are our big players in the game. C2 has flow disabled, C6 has flow and turbulence disabled, and then C9 has flow, turbulence, and the calculation of our moments disabled. Here you can see results of a 1500 time step benchmark. So essentially, how fast can we calculate 1500 time steps? What's the solver rate? And you can see highlighted in the green that our C2 has a rate of around 6.1 time steps per real second, C6 6.25, and C9 6.47. And you might be thinking that's not very much of an increase, and that's because it isn't, but trust me, it gets better. We'll get into that. But you can see, as we disable more and more, we decrease the amount of time. The reason that those are our big players is if you look at data for time to kinetic convergence, all of the other simulations, apart from the base, they didn't diverge and explode, but they were fairly consistently departing from our target value. So for the time being, they're not our main focus. And these C2, C6, and C9 simulations are about 0.0368% error from our target value. So again, our kinetics are not being affected, which can be seen with the amount of time steps it takes for each of these to reach QSS. Even though the rate of the solver is increasing, they take the same amount of time steps. So, which is again supporting the idea that if you're disabling equations and features that have converged or reached QSS, you're not affecting the kinetics of the actual simulation. Here we have that same PDI chart over time. This is from our base case with no PEM implemented, so nothing's disabled here. You see it took that around 478 time steps to converge. And again, this is in our 3-cell CSGR. This is what all of our tests are being run right now. And this is with PEM C9 being enabled. So that whole flat portion at the top is C9, where our moment equations, turbulence, and flow are all turned off. But of course, to calculate PDI, you need to enable those moments, which is where we switch to C6 around 3/4 of the way through, just to get those moment equations calibrated. And you can see that the PDI quickly catches up and adapts to this new thermal and species concentration field, and we still get to our final PDI 0.03% away from our target value in the same number of time steps. And then here's where it actually gets significant and important. If we scale up these simulations, so if we simulate in more than just our 3-cell model, you can see here we have cell count on the x-axis and percent speed increase from the base with nothing disabled. As we add more and more cells, your percent speed increase is also increasing. And in our 5.7 million cell industrial scale reactor, we have a fit curve projecting that will have a 105% increase in speed. And you'll also notice that these fit curve lines start to converge near the top, so the difference between all the cases seems to lessen and lessen. And to confirm that these fits were accurate, they have R-squared values around 0.987, but we wanted to confirm that they were still accurate, so we quantified the ratios between different cases and their speed increases to each other. So this is just showing that as you increase in cell count, the difference in speed between each of these cases from each other is decreasing. So that was observed here and in the last plot, so we're confident that that is an accurate behavior. So in conclusion, pausing calculations that have reached QSS, so example flow and turbulence, will not affect kinetic convergence. Calculations of polymer moments can be paused and then re-enabled since those values don't contribute to the actual reaction as it's developing. And once they are re-enabled, they readapt to the new concentration and thermal fields quickly, producing those transient stair steps of polymer properties. So if you recall in our 3-cell model, we had a long flat portion and then it dropped. If we implemented that into a full-scale reactor and cycled this enabling and disabling just to check on it, you get that stair step look like we were looking at earlier on. And finally, using the PEM we have now, we are projected to take a year off of our reactor scale simulation. And this research is fairly new, so we're of course still looking for ways to improve upon this number. In the future, we want to test on more CSTRs with varying cell counts just to develop stronger fit curves and get more of an idea of where we're headed once we scale this up. We also want to alter the PEM cases that didn't converge to the correct values. Those ones that were diverging from our target values, we may be able to increase mass diffusivity, discretization schemes, and more to get them down to the right number. And finally, of course, we need to implement this into a full-scale reactor model in the future. Thank you so much for your time. Take any questions.